Hello, this is Kevin Iga. Welcome to these lectures given online for Math 141. Hi, I hope everybody's safe and found a place to be comfortable. I hope you're with family or friends or both. We'll try to get as much done these weeks before we return. Just so you know how things are laid out, normally we would have had our exam on probability distributions, conditional probability, all that stuff. Um, we didn't have that exam. We will have that exam when you get back on Tuesday. Actually, I decided not to put it on Monday when we get back. So there's a possible chance for you to ask questions, things like that. And so on Tuesday we'll have our after Thanksgiving is when we will have our exam. In the meantime, I'm going to have to give some lectures to cover some material that we normally would have had after our exam. So normally after that exam, we would um, focus on the third part of the course. The first part was multivariable calculus. The second part was probability. And this third part is about matrices. So this is not at all connected to the stuff that you are going to be tested on your exam. Hopefully, this won't cause any confusion. So continue studying for your exam, and you can continue asking questions about it and that sort of thing. But yeah, in the meantime, we are going to cover more material. So we're going to go back to chapter 2. We skipped chapter 2 a while back. We're going back to it now, and that's what we're going to be doing. Okay, so um, returning to chapter 2, this is about matrices. Okay, and so what's this about? A matrix is a rectangular block of numbers, like here. Okay, we've got 3 rows and 4 columns with numbers in it, and usually put either parentheses or brackets in this case around it just to set it aside so we know that that's one object. Okay, the singular is a matrix, so this is a matrix. The plural is matrices. Now, matrices are a pretty simple idea. You just put numbers in a rectangular block like this, but it's amazingly powerful. It's used in all sorts of applications in science, engineering, mathematics, and even in business. So, business, they're used to do things like scheduling resources. So, when you have, say, for instance, scheduling people or scheduling use of equipment, things like that. There's a whole thing called the simplex method that relates to problems like that. Describing supply chain or distribution chain relationships, networks, things like that. Well, today we're going to introduce matrices using one of the most iconic applications of matrices, and that is solving systems of equations. In particular, solving systems of linear equations. All right, so systems of linear equations. I have to say what that means. An equation, of course, as I said before, an equation is anything with an equal sign, so like that, right? A linear equation is an equation. Well, you're used to these kinds of linear equations: 3x plus 5 equals 1. But actually, you're allowed to have linear equations with more than one variable, like this: 3x plus 2y plus 5z equals 10. That's an example of a linear equation with 3 variables, x, y, and z. The key thing is what's not linear. Like this x squared here, that's not linear. The e to the x, multiplying two things that are not constants, that would make it nonlinear. Okay, so each term in a linear equation is either a constant times a variable, like this 3x or 2y, so stuff like that, or just a constant, so things like 5, 1, 10, and you add them or subtract them, and that's a linear equation. Okay, so that's a linear equation. What's a system of linear equations? A system just means more than one. So here we have 2 equations. Okay, and so a system of linear equations means 2 or more equations where they are each equation is linear. When we talk about a solution to a system of equations, it just means x is equal to this, y is equal to that. It's assignment to each variable what they're equal to. Okay, so this is a system of linear equations. It turns out x equals -7 and y equals 6 is a solution. What that means is when I plug x equals -7, and then here and here, and I plug y equals 6 here, here, and here, I get these equations, and it turns out both of these equations are true. You can go ahead and check that if you want. That means this is a solution. So a solution is an assignment of what is x, what is y, and so on for every variable in such a way that all the equations are true. Notice, by the way, x equals -7, y equals 6 is one solution. Sometimes people, students mistakenly believe that this is two solutions because you've got two equations here. Actually, no, this is one solution. A solution, remember, is an assignment of a number to every variable. So there's x and y, those are two variables here. This is a single solution. And at some other point, we might talk about equations that have more than one solution, but this is one solution. There are lots of different ways to find solutions. You no doubt know many of them. Here is one famous one. We've already used this one earlier in the course. So substitution. So here's our problem. Here's our system of equations. And you just take the first one, and we simplify it a little bit. We're going to move the 2 to this side of the equation and the 5y to this side of the equation. That means subtracting off 5y, subtracting 2. You have a 2x remaining. The y minus 5y combines to a -4y. The 12 minus 2 combines to make a 10. Okay, so you get this equation. Then we're going to divide both sides by 2. We get x equals -2y plus 5. Just divide everything by 2. Okay. And if you know the process called substitution, you know that this is exactly what we've been hoping for. We have x equals and then something that doesn't involve x. And the idea here is we can use this to eliminate x. Anywhere else where we see x, for instance, this equation we haven't used yet, we're going to stick in this for x, and then we won't have any x's anymore. So we get 5y plus 3. Instead of x, we write -2y plus 5 here. Minus 9 is equal to 0. Okay. And then from here on out, this is just one equation with one variable, and you can solve it. Just multiply this out, combine terms, you get y equals 6. And y equals 6 is not a solution, because a solution means you have to say what all the variables are equal to. So y equals 6, that's not all the variables, there's also x. So I have to plug this into here to get what x is. X equals -2 times y, which is 6, plus 5. Plug it in, you get -7. So x equals -7, y equals 6 is a solution, as I explained, or as I foreshadowed earlier. All right, so this is one of the many ways to solve this system of equations. I'd like to teach you a new way, a different way than this one. That might raise the question, why? So this method works. Why do we need another method? Okay, the reason why we need another method is we want a systematic approach. Okay, we don't want to just say, well, try this, try that, wander around. Eventually, we get an answer, or we hope to get an answer. We want something where you do this step, then do that step. Okay. You no doubt have seen in your earlier mathematics examples of problems where you're supposed to just do this, then do that, and here's the answer. And other problems where you just mess around for a while and you hope you figure out what you're supposed to do, and eventually you hope to get the answer. Obviously, the first type is easier to deal with, and that's what I mean by systematic. Okay. The key here is a systematic approach does not require that we be clever in the middle of the problem. Like some problems require that you just kind of figure out things, and maybe if you see the right insight, you can do the right thing. But a systematic approach means you can just do the problem step by step. Okay? So in particular, you can get a computer to do it. Okay? A computer just does what you tell it to do, and the idea is, in this case, we want a method that will do the problem. You just do this step, then this step. You just tell the computer ahead of time what the steps are. And in particular, we don't need to be clever. It means also that we're guaranteed to get the answer, right? I mean, if we didn't have a systematic approach, we might just not be clever enough, and then we don't know if we find the answer. But in this case, the idea is we want a method that will find an answer. There are situations where you might have more variables or more equations. That one had 2 variables and 2 equations. You could have say, 10 variables or 30 equations. And for that, I mean, sure, you could try to do the method that I described, but it sounds like you just kind of chase yourself in circles. It's not clear if you'd ever find the answer. It would be certainly convenient if we could get a computer to do it for us. And so that's what this new system, this new method should do for us. By the way, there might be, in some cases, especially depending on how many variables or equations there might be no solution. And the other methods, maybe you might not discover that that's the case. But in this method, you will know, it will tell you directly there is no solution. Also, there might be more than one solution. And so the other methods, maybe it might be hard to see that. But in this method, it will tell you precisely what all the solutions are. So this method, what is this method all about? Well, that's the topic for today. It goes by a number of different names. Elimination or row reduction are some of the names. Very commonly, it's called Gaussian elimination or sometimes Gauss-Jordan elimination. It's often named after the mathematician Carl Friedrich Gauss, who's a very famous mathematician. It turns out, although he used this method, he did not originate it, nor did he claim to originate it. It's been used by Isaac Newton, other people for hundreds of years. Nobody really knows who came up with it first. The first record we have of it is from a 2nd century Han Dynasty Chinese text. Most likely this is an idea that has been invented and reinvented many, many times over the centuries. Anyway, sometimes I'll tend to call it Gaussian elimination because that's what I called it when I was learning the material, and the book uses that term too. Even though it's not quite historically accurate. All right, how do we do it? First of all, you put your equations in standard form. This is pretty easy. This is something that you probably all do as a matter of course. We want to move variables and constants so that the similar things are together. So we're going to move all the variables on the left and the constants on the right of side that equals. So let's say this is an example of an equation, a linear equation, and things like 5 is a constant, so on the wrong side you just have to put it on this side. So I subtract 5 from this side. And then 5z, well, that's a variable, that involves a variable, so that's on the wrong side. I got to move it, subtract 5z to put it on this side. And also 8x and 2y. We want to put the variables in some kind of order, and I used alphabetical order. I mean, that's not a requirement, but it helps to do that so that you're always using the same order in every equation, and alphabetical order is a good way to do that. So this is going to be 8x plus 2y, put the x ones first and then the y, then the minus 5z, the z comes last, and then the 7 minus 5, or 2, comes on this side of the equation. Okay, so this is what I mean by putting equations into standard form. In our example, we had this system of equations. Okay, you'll notice that there are 2x is over here, and then there's a y on this side. So I'm going to bring the y to this side. 5y minus y is 4y. So the 2 is on the wrong side. Subtract 2. 12 minus 2 is 10. So you see, you get 2x plus 4y equals 10. Notice I've changed the order of x and y here to be in the standard alphabetical order. Same with this one. The 3x and 5y are in the wrong order, so I'm going to put 3x plus 5y here. And the 9 is a constant, should be on the other side, so I add y to put it on this side. All right, so now that's our first step. We've put it into our standard order. Our second step is the longest step. We're going to do a whole bunch of steps here. Okay, there are operations of 3 different types. elementary operation 1, elementary operation 2, elementary operation 3. Elementary, by the way, does not mean easy, although these are easy. What they mean by elementary here is that this step is going to be broken up into small pieces, and elementary is elementary in the sense of these are the smallest pieces that we are going to break things up into. Okay, and elementary operation of type 1, swap two equations. Elementary operation of type 2, you're going to multiply an equation by a number on both sides. That number has to be non-zero. And elementary operation type 3, we're going to add a multiple of one equation to another. So let me illustrate these operations with some examples. So let's say we have this system here. This is the system that we were dealing with just recently. We can swap the two equations. Obviously, that doesn't do very much, right? It's basically the same system. It's just we put the equations in a different order. So there's not much to say about that. That's pretty easy. That's called elementary operations of type 1. Elementary operations of type 2 means we're going to multiply an equation by a number. So here again is that example system, and we can multiply one of these equations, say the first equation, by a number. For example, we could multiply it by 1/2. If I multiply this by 1/2, okay, then this becomes, instead of 2x, it becomes 2 divided by 2, or 1x. This 4y becomes 2y. The 10 becomes a 5. This other equation remains exactly the same. So that's what I mean by I say multiply the first equation by 1/2. What I'll do is I'll use brackets to indicate an equation number. So here it's 1/2 bracket 1 means 1/2 times equation 1, and this is how I'm going to notate this kind of operation. Multiply this equation by this number 1/2. All right, that's elementary operations of type 2. Elementary operations of type 3. Add a multiple of one equation to another. Okay, again, this is our sample system of equations. And in this example, I'm going to add 5 times the first equation to the second equation. So I'm going to multiply these by 5 and add it to these numbers here. Okay, so 5 times 2x is 10x, plus 3 is 13x. So that's why they put 13x here. And then 5 times 4y is 20y, add it to this one, to 5y is 25y. And if I do it this, 5 times 10 is 50, add it to 9 is 59. Now, you will notice that this first equation remains the same as before. Okay? Sometimes students are a little confused by this. The point is we are not actually multiplying the first equation by 5 and then stopping. We are taking whatever 5 times the first equation is and adding it to the second equation, but the first equation remains as it is. Okay, so the first equation remains as it is. The second equation, we modify it by adding some multiple of this one. In this case, 5 times this one added to this one. One thing, by the way, this is the notation I'll use: 5 times row 1 plus equation 1 plus equation 2, and this means this operation. If you had an x and a y that satisfied this system of equations, then this would be true and this would be true. And multiplying it by some number like 5 would make, again, a true equation, and adding equals to equals also gives us something that's equal. So anything that solves this system will solve this system as well. And the other thing is these are all reversible. So first of all, if what I said, if a solution makes the original true, then it makes the new system true. This is true for any of the operations that we looked at. So these operations do not change the set of solutions. Whatever solutions you had originally, the new thing will have the same solutions. And these operations are reversible, so they work the other way too. So any solution of the new one is also a solution of the old one as well. All right. So here's the thing. This procedure is potentially cumbersome. Well, it is cumbersome. And it helps if we don't have to write down everything. Like these x's and y's, I mean, we all know that where they are, and the plus, we know that where that is. So we're just going to put these numbers. That's all we're dealing with, right? These numbers are what we're going to be manipulating. And so we're going to put it in a matrix like this. You put the coefficients of x here, the coefficients of y there, and the constants here. These equations now correspond to rows. This first row is the equation 2x plus 4y equals 10. This second row is 3x plus 5y equals 9. That's how you read this. I put a vertical line here, and the vertical line is just a reminder that where the equal signs go. Okay, we're not going to really do anything with that vertical line. This is called an augmented matrix. Okay, just adding this line here. But other than that, this is basically a matrix. You've got rows and columns of this matrix. Once I write it like this, I can rephrase all of my elementary operations and turn them into operations on these matrices. So if you remember, the original operation, elementary operation of type 1, swapped two equations. Now we're going to swap two rows. And instead of multiplying an equation, we're going to multiply a row by a number. You multiply all across by a number. And operations of type 3, we're going to add a multiple of one row to another row. So I'm going to illustrate this, okay? And I'm going to illustrate this by some examples. So this is the example that we were working with. I'm going to multiply row 1 by 1/2. You notice all these numbers multiplied by 1/2. 1, 2, and 5, like that. That's how this goes. Now, you might, at this stage, ask, how do I know which type of operation to do? Fair enough question, but I'm not going to answer it right now. I'm just going to illustrate the use of these operations, and then once I have a bunch of these done, then it will be easier then for me to answer what operations we do when. Okay, so for now, it's going to be mysterious. Why did I choose this operation? Why not an operation of type 1 or type 3? I'm gonna answer that later. So here's an operation of type 2, and I turn this into this. The idea is now I start with this one, and I'm going to do a different operation. So here it is, 1, 2, 5, 3, 5, 9. I'm going to do now an operation of type 3. And this one is going to add -3 times the first row and add it to the second row. So that's what I wrote, -3 times the first row added to the second row. Notice that the first row stays the same, 1, 2, 5. The second row changes. -3 times 1 is -3, added to 3 makes a 0. -3 times 2 is -6, added to 5 is -1. -3 times 5 is -15, added to 9 is -6. So now I'm going to take this resulting matrix and now use that in my next step. Okay, so this is the resulting matrix. I'm going to now do an operation of type 2. I'm going to multiply this second row by -1. So -1 times row 2. And this becomes 0, -1 and -6 become 1 and 6. The first row remains unchanged. So you have this. And now we are going to do one more row operation. We're going to add -2 times the second row added to the first row. When I do this, -2 times 0 is 0, added to 1 is 1, so that stays 1. -2 times 1 is -2, added to 2 is 0. -2 times 6 is -12, added to 5 is -7. And so we have done a bunch of these row operations. Which row operations did we do? Why did I choose those operations? Like I said, I'll get to that in a moment. But for the moment, all I want you to see is you can do these operations and end up with a new matrix. Once I have this new matrix, I can turn it back into equations. Remember how to read these matrices as equations. It's this times x plus this times y equals that. So this is 1 times x plus 0 times y equals -7. The second row reads 0 times x plus 1 times y equals 6. You look at this and you realize that just says x equals -7, y equals 6. Which is, of course, our answer. This is our solution. That's kind of amazing. Just suddenly the solution drops out of this whole process at the end. Okay. What happened? Well, one thing that's important is this last step. This last step had ones and zeros in just the right places. This one said x because there's a 1x plus 0y. And this one said y because it said 0x plus 1y. It was important that there's a 1 here and here and the zeros here and here. That's how this all happened. Okay. Now, in a way, this is a little bit like these puzzles. For example, maybe you're familiar with the Rubik's Cube. In the Rubik's Cube, you've got this cube that you can turn things, and you've got colored squares, and you're supposed to do all these turns and eventually solve the puzzle. And the way you solve it, I mean, the solution looks like on each side all the colors are the same, or all the squares are the same color. Okay. Now, any of you who have played around with this might realize it's a pretty difficult puzzle to solve. Don't worry, this Gaussian elimination is a much easier puzzle than the Rubik's Cube. Okay, and when you solve the Rubik's Cube, one of the things that you have is you have certain moves that you're allowed to make. For instance, you can turn the top face or the front face or the left face and so on. But you're not allowed to say, take a hammer and smash it and take out the pieces and put it back together. That's not allowed, right? So certain operations are allowed, certain operations are not allowed. Well, we've got that situation here. We've got 3 kinds of operations that are allowed. Now, some of these operations, if we do them, we'll get closer to an answer. Some of them, if we do those, we will get further from an answer, or at least maybe spin our wheels, not actually getting anywhere. So there are several things we need to understand. We need to know what we're allowed to do. Those are the row operations. Where we're trying to get to, and that's this pattern here: 1s over here, 0s over here. And then we need a strategy. We need to know what rules, what row operations we're going to use, and in what order to get it to this state. Okay. Here, by the way, is a summary of what we did, so we can kind of look at it. Here's what we started with. Then we did this row operation, 1/2 times row 1 to get this one. Then you did this row operation to get to this next one. Then we did this row operation to get to this one. And eventually you had this pattern here. Okay. How do we do this? Well, let me tell you what order we're going to solve this in. We're going to turn all of these into 1s and 0s. These are being 1s, these being 0s. But it's important that we do it in the right order. We do it in this order. This, then this, then this, then this. So start from the upper left, turn the 2 into a 1, turn the 3 into a 0, turn the 5 into a 1, turn the 4 into a 0, like this. Let me show you that that's what we did. So we started with this. We turned the 2 into a 1 by doing this operation. 1/2 times this certainly turns 2 into a 1. It also does things to the other numbers, but never mind that for now. You will notice something interesting. Once I do that, this 2 turns to a 1. This 1 stays as a 1 for the rest of the problem. Okay, this happens if you do it in the right order. If you do these in the wrong order, then this is going to get messed up. So you might, those of you who played around with Rubik's Cube might know this feeling. You try to make one of the faces all red, for example. Well, then in order to actually get any of the other faces or any of the other pieces in the right order, it turns out you're going to have to mess up what you started with and somehow get it back again. And that's what makes Rubik's Cube really complicated. Actually, if you do this in the right order, that never happens to us in Gauss elimination. Okay? Once I get this here, if I do it in the right order, these will stay here. The next thing to do is to turn this 3 into a 0. And indeed, once I turn it into a 0, the other operations that have to do later on turn out not to affect these this 0. Then I wanted to make this -1 into a 1. And once it's there, then it continues that way. And then finally making this 2 into a 0 like this. So that's the order. First, this one upper left becomes a 1, then the lower left, then the bottom right, and the upper right. Okay. Do it in that order. If you don't do it in that order, then each subsequent move might mess up some of the things that you already accomplished. Do it in this order. All right. The next question I'd like to address is which type of operation should we use? For instance, here I use an operation of type 2. Here I use an operation of type 3. Here's the rule. Whenever you want to get a 0, use an operation of type 3. Whenever you want to get a 1, use an operation of type 2. Okay? So sometimes we want a 1, sometimes we want a 0, and this tells us which operation type we're going to use. The operations of type 3, whenever I 0, operations of type 2, whenever I want a 1. You might wonder what happened to operations of type 1. Actually, if you look through, we have not used operations of type 1 yet in solving this problem. And indeed, it's not necessary to solve this problem. It's often not necessary to solve these problems, but occasionally there are situations where it is necessary. And I want to talk about that on some other day. For now, we're going to ignore operations of type 1. All right, let's review our steps. First, we use an operation of type 2. Why? Because I want to turn this into a 1. So I use an operation of type 2. Operation of type 2 says multiply this by a number. What do I multiply by? Well, whatever is going to make this a 1. See, I have a 2. I want a 1 multiplied by 1/2, right? So that's exactly what I do. 1/2 times row 1. Multiply it through, I get this. And now I've accomplished this 1. And now I want to make this 3 into a 0. Now to get a 0, I use an operation of type 3. So I take negative 3 times the first row, add it to the second row. Okay, so this row stays the same, but this one takes negative 3 times this and adds it here. Now this will turn negative 3 times 1 is negative 3 plus 3. This makes this a 0. That's why I chose negative 3. Right? I want to make this a 0. What do I have to multiply this by and then add it to this to make 0? Well, I have to multiply this by negative 3. That's why I chose negative 3 here. Okay? And of course, these other things will put other numbers here. And now I look at this and I want to turn this into a 1. I have to divide by negative 1. So multiply by negative 1 here. And I get this. Now this is a 1. And now I want to make this a 0. So this times something plus this is 0. So this times negative 2 plus this is going to be 0. In general, it's going to be just the negative of whatever's in here. And you just do that. And negative 2 times the second row added to the first row, and we get this. So hopefully now I have answered the question, how do we know which operation type to use? Yeah, I told you the order in which you should look at these, what you're trying to achieve for each of these. And if you're trying to get a 1, you use operations of type 2. If you're trying to get a 0, you use operations of type 3. And you do it in this order, and you will end up with the solution here. All right, your turn. Here's a system of equations, and I want you to solve it using this method. So first you're going to turn it into a matrix, and then you're going to do these elementary row operations until you get the 1s and 0s in the right place. And then turn it back into equations, which would give you your solution. You might want to go back and review the previous parts of the video in case you want to remember which things you do when. And when you're ready to do this problem, pause the video, and then I'll tell you how to do it. Okay, ready and pause. All right, so if you're back, and hopefully you've been able to figure out how to do this problem, let me walk you through the answer. So the first step is you have to turn this into a matrix, and you do it like that. Okay, these numbers 3, 6, 9 go here, 2, 1, 5 go here. Notice there's no 1 here, but I know there's a 1 that's hidden, so I write 1 here. And now, here are the steps. Here are the row operations. I want to make this 3 into a 1, so I use an operation of type 2. It's 1/3 will do that, turn a 3 into a 1, and these numbers turn to whatever they turn into. Then I want to get the 2 into a 0. So I'm going to take negative 2 times the first row, add it to the second row, like this. And indeed, that makes 0. Remember, I'm using an operation of type 3. Now I want this to be a 1, so I use an operation of type 2. Multiply this by something. What should it be? Negative 1/3. That'll turn a negative 3 into a 1. And indeed it does. At the expense of turning this into 1/3. That's okay. And then last I want to make this 2 into a 0. So I'm going to use an operation of type 3 again. This time using this, multiplying this equation, or this row, by a number to add it to this one. Which number should it be? Well, negative 2, of course. It's just negative of this number. Negative 2 times this row added to this row gives us this. And that should give us this matrix. Write down this matrix, turn it into x and y, that is, turn it into this equation. It says 1x plus 0y equals 7/3, so it's x equals 7/3. This one says y equals 1/3. And there is your answer. All right, so now you should know how to do Gaussian elimination, at least for this special case, with 2 equations and 2 variables. Now, 2.1 actually talks about a few more other cases, and I will be talking about some of those other cases. In the meantime, you've got homework that's due tomorrow. I'm actually going to allow you to turn it in until Sunday, but you should actually try to do it for Friday. And next time we'll be doing more general things. So just to make sure you keep up with things, do your homework before tomorrow. That way you'll be ready to understand the next more complicated versions of this procedure. All right, I'll see you next time.